So we've been looking at limits numerically and graphically. So those are ways of estimating the value of a limit. And we're trying, again, if you think about it, what is the function, what is the value of the function trying to obtain or get to as x approaches a? That's what we're talking about when we talk about the limit as x approaches a of the function. And we can, we looked at that numerically, right? Just plugging in values close to a for x and seeing if the value of the function appeared to be getting closer and closer to some value. And then we looked at graphically, right? Just looking at the graph of the function. So now we want to transition and look at how do we actually find the exact value of the limit. And we're going to be doing that algebraically. We start off real simple though with these basic limit laws here. And so we'll just go through this list real quick here. If a and c are real numbers and n is any positive integer, then we have these following basic limit laws. The limit as x approaches a of a constant is the constant. Well, think about what that would look like graphically. We've talked about graphical situations, right? What is the graph of the function f of x equal c look like? What's the graph of that function look like? Well, for any input, what's the output? C. It doesn't matter what I put in here. F of 1 is C. F of negative 3 is C. F of 2 is C. F of 0 is C. F of anything is C. All right, C is some constant, some fixed value. Let's suppose C is positive. So here y is C. Then the graph of this function would simply just be what? Just a horizontal line. Right, just a linear function effect. It's the graph of a line with slope 0, right? And so there it is. And so if a is some value, whatever it is, let's say it's a positive value, what value is the function trying to obtain? What value is the function trying to obtain? Well, it's obviously as x approaches a, right, getting from the left, from below, then we're on here. Our table values would just be what? C, 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 C. What are we approaching? C. From the positive side, if I approach A from the positive side, then we're on the graph here. Right? The values again are always C, C, C. We're going right to this point. It's obvious that as x gets closer in A, and we're on this graph, where are we going to? We're going right to that point, which is on the graph, which is has a height of C. And so that's why the limit as x approaches A of a constant is always the constant. The limit as x approaches a of x is equal to a. And again, we can look at the graph of the function f of x equals x. Right? What's the graph of the function f of x equal x look like? Well, it's a line of slope 1, right? 1x plus 0, y-intercept 0. So it's a line of slope 1 passing right through the origin. So here's the graph of our function. And again, if I have some value a here, right, then as x approaches a from the left or right, where are we at in the function, right? So where are we going to? Well, obviously we're going right to that point on the graph, right? As x approaches a from below, where are we going to? We're going right to the y-coordinate of that hole. What is the y-coordinate of that hole? Or sorry, hole, point. It's not a hole, it's a point, right? Well, obviously, what is f of a? F of a is what? A. So input A, output A. So we have a height of A. Right? And as I approach A from above, same thing. I'm going right to that point, which has a y-coordinate of A. And therefore, the limit as x approaches A of x is A. Similarly, the limit as x approaches A of x to the n, remember n is any positive integer, is A to the n. And then we'll look at one more example there. Let's look at the case for n equal 2, right? So if I'm thinking about the function f of x equals x squared, then what's the graph look like? You should know it's a parabola opening upward, right? With the vertex right at the origin, 0, 0. So here's our graph. And let's pick a point A here, all right? Now, before we talk about the limit, let's talk about what's the value of the function at A. If I plug in A into the function, what's the output? What is my height going to be? Plug in A, what do I get? A squared. Right? A squared. And so again, as I approach A from below, where am I at on the curve? I'm going right to the y-coordinate of that hole. As I approach a from above, the value of the function is getting close to what? The y-coordinate of that whole, which is what? A squared. So the limit as x approaches a of x squared would be a squared in that case. And that's true for any value of n. Okay, so we'll talk about these three together, and they're part of a more general statement that we can say that we'll be able to talk about after we talk about continuity. Number 4 has quite a bit. Now let's change modes. This starts with two functions f and g that we know have the following limits. Real important, they have the limits. That the limit as x approaches a of f of x equals L, the limit as x approaches a of g of x equals m. So as for whatever the function is, as x approaches a, then we're approaching the value of L, right? And similarly for g, we're approaching a value of m. And so in that case, we have the following. The limit as x approaches a of c, which is a constant, times the function. So a constant multiple function. That constant can come outside the limit, and we just take the limit as x approaches a of the function f of x, which we know is L. So in other words, the limit of a constant times a function is the constant times the limit, provided the limit exists. Case B here, there's actually two things here. The limit as x approaches a of f of x plus g of x or f of x minus g of x is the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x, which is of course L plus or minus m, provided those limits are as stated. So again, this says the limit of a sum of functions is the sum of the limits, or the limit of a difference of functions is the difference of the limits. Here we have a limit of a product of product of two functions. Well, provided the limits exist, then this will be equal to the product of the individual limits of those two functions, L times m. And the limit as x approaches a of a quotient or a division, right, problem, f of x divided by g of x, the limit of that is the limit of the one function over the limit of the other function. Now this does have a restriction, right? Provided m is not 0. We could have the limit as x approaches a of g of x be equal to m. I mean, that would be a valid situation perhaps. But obviously we would have problems with this case if m were indeed 0. If we were dividing by 0, then we don't have a real number. E says the limit as x approaches a of a function raised to some, remember n is some positive integer, so for any power, we can bring the limit inside, right, and take the limit as x approaches a of f of x and then raise it to that power. Right? Of course, the limit as x approaches a of f of x we said was L, and so we're getting L to the n. Okay? And then we have, similarly, if we have the nth root of f of x, the limit as x approaches a of that is the nth root of the limit. There are some restrictions, obviously, depending on whether n is even or odd, because square roots, fourth roots, and so on. The value of L could not be negative, otherwise we would not have a real number there. Taking the even root of a negative number is not a real number. Now, important that if either one of these limits actually does not exist, and we've talked about cases where limits do not exist. We talked about in general, we can have a limit from the left exist, limit from right exist, but if they're not equal, then the limit does not exist. Or we had even a case we looked at the end of the last video where we had this strange function that had this infinite number of oscillations where we never settled down to any value and the limit did not exist. Either case, if one of these limits do not exist, then we cannot use these limit laws. We got to be careful. They are not necessarily true. They are only true, right, when these two limits exist, provided these limits exist. All right, so let's see if we can put all this together that we've learned. This is it. This is the basic limit laws. This whole section, which is 2.3 in the book. So what do we have? What's the limit as x approaches 3 of 10? Well, 10 is a constant, right? So it's this first relationship here. Limit as x approaches a of a constant is a constant. So this is going to be equal to 10, right? So the function is f of x equal 10. So no matter what I approach, right, I'm always at a height of 10. The limit as x approaches 3 of x is just going to be 3. 3. And that's using this second limit law right here. And then obviously we're going to use number 3 here for this last one. The limit as x approaches 3 of x squared is 3 squared, which of course is 9. So very easy to find these limits. These are basic limit laws. They are very basic and easy. Okay, let's look at some other. Now I'm going to make use of the limits, basic limit law of number 4 here on this one. And I'm going to do it in all of its wondrous glory, each step by step. In the future we won't need to do all of this, but I do want to show you how all these limit laws come into play here. So first of all, the limit as x approaches -1 of x squared minus 5 divided by 2x plus 4. Well, first of all, we have a quotient. So look at this. I can use part D to say the limit of a quotient is the quotient of the limits. So I can write this as the limit as x approaches -1 of x squared minus 5 over the limit as x approaches -1 of 2x plus 4. Okay. Now up top I've got the limit as x approaches -1 of x squared minus 5. I can use part B where f of x is x squared and g of x is 5 and write that as the difference of the limits. Similarly down here, limit as x approaches -1 of 2x plus 4, I can make use of B as well to write that as the sum of two limits. So let's do that to the right here. So making use of 4b here, I have the limit as x approaches -1 of x squared minus the limit as x approaches -1 of 5 over the limit as x approaches -1 of 2x plus the limit as x approaches -1 of 4. Okay. Now, let's look at this first limit here, limit as x approaches -1 of x squared. I can make use back here of number 3 and find that limit, right? I can just simply replace x, in this case, with -1. My value of a is -1 here. And so I'm going to get what? -1 squared. What's the limit as x approaches -1 of 5? Well, that's my constant rule at the very beginning, right? The limit as x approaches a of a constant is the constant. In this case, the constant is 5. So the limit as x approaches -1 of 5 is indeed 5. Now this, let me just say, I can take this and make use of limit law 4a. The limit as x approaches a of a constant times a function. The constant can come out. The constant in this case is 2. It's 2 times x. So this is 2 times the limit as x approaches -1 of x, right? And so what's this going to be? 2 times what? What's the limit as x approaches -1 of x? Well, by property 2 right here is x approaches a. The limit of x is just equal to a, and basically replacing a, in this case -1, replacing x with -1. Plus, what's the limit as x approaches -1 of 4? Constant rule again, that's just 4. Okay. And now I can simply do the calculation, right? -1 squared is 1. 1 minus 5 is -4. 2 times -1 is -2 plus 4 is 2. And so I get -2, and that is my limit. Notice I could do this because these final limits that I calculated in each case to get these values here all existed, right? Provided those limits exist, we can do this. Okay. Now, someone might just say, hey, it looks like almost I can go right from this expression to this one by just doing what? Replacing x. Everywhere I see an x, I'm just going to replace it with -1. And I'll get this right down here. And you are correct. You are correct. And so what we're going to see is this type of function here is what we call continuous at x equal -1, or this function is continuous at x equal -1. And we will be able to find limits that are continuous by simply doing exactly that, direct substitution. But when we do direct substitution, what was really going on is these limit laws, right, that we've talked about. All these limit laws that we've talked about is what's going on. But as long as we're continuous, as long as we're approaching right, a point that's actually on the graph, as long as, a point that's, right there at that location, not like a hole. We've seen graphical examples where we have holes in the graph. We might have to do some other kind of work there than the basic limit laws algebraically, and we'll be talking about those later. Okay, but yeah, we'll get to that in the next video when we talk about continuity, about how we can use direct substitution. But I want to show you what's really going on there. Also, it's helpful to use the basic limit laws in the same way as I did above. In this case, here I say, suppose the limit as x approaches 2 of f of x is 5, and the limit as x approaches 2 of g of x is negative 6. Find this limit. Well, here's where we're going to have to use those basic limit laws again. And so what we're going to have is, again, the limit of a quotient is the quotient of the limits. I guess I'm going to do this one more time. I said I'd maybe only do it once, but in these ones you really have to do it in the sense that we see all the limit laws. All right, so the limit of a quotient is the quotient of limits, and then the limit of a sum is the sum of the limits. And the limit of a difference is the difference of the limits. Okay, so hopefully everyone's followed that. So limit of a quotient, quotient of limits, limit of the sum or difference is the sum or difference of the limits. So maybe use the properties for D and then for B. Okay. Now, I'm going to make use of property 4A right here and say that this is 2 times the limit as x approaches 2 of g of x. That's that constant multiple rule. I can pull that constant out. This one we know, the limit as x approaches 2 of 15, that's a constant. That's just 15. Down here, I've got the limit as x approaches 2, of 20. Well, that's just 20, right? That's just a constant. And then what about this one here? Limit as x approaches 2 of f of x squared. Well, I'm going to make use of this rule right here for E that says the limit as x approaches a of f of x to the n. I can bring the limit sort of inside, right, the exponent n. So this becomes the limit as x approaches a of f of x. So I'm going to write that as minus, in parentheses now, the limit as x approaches 2 f of x all squared. Okay. Sorry about that. And now what do we do? Now we can go back to the original information. We know the limit as x approaches 2 of f of x is 5, right? So this is equal to 5. And the limit as x approaches 2 of g of x is negative 6. So this limit here is negative 6. Both these limits exist, so we can make use of these limit laws that we've been making use of to get to this point. And now I can calculate. 2 times negative 6 is negative 12. I've got 20 minus 5 down below. And what do I get? Negative 12 plus 15, that's 3. Whoops, I said 5 squared, sorry. 5 squared. Negative 12 plus 15 is 3. 20 minus 5 squared, what's that? 20 times 20 minus 5 squared, that's 25. 20 minus 25, negative 5. So negative divided into a positive is a negative number. So with all that, our limit is negative 3/5. Okay. And those are the basic limit laws. Very basic, very easy. What we'll look at next is this idea of continuity and what that's all about. And then we'll continue how we would find limits algebraically for cases where the basic limit laws don't apply.